In all the previous definitions of security that we've talked about for private key encryption, we've been implicitly or explicitly assuming only a passive eavesdropping attacker. In pictures, what this means is that we have an attacker who can eavesdrop on the communication channel between the sender and the receiver, looking at the ciphertexts that are being sent from one party to the other, and our definitions of security then require that it be infeasible for the attacker who's observing those ciphertexts to figure out any information about the messages that were being communicated. We can ask, however, what about if we consider stronger attack models? For example, an attacker who can be active and actively sending communication on the communication channel or interfering with the communication on the communication channel. So if we look at the first case of an adversary interfering with the communication channel, we get a picture something like this. So here we again have our two parties who have shared a key K in advance and who wish to communicate. And we have the sender taking their message, encrypting it, getting a ciphertext, and then sending that to the receiver across the channel. Now, however, we do not assume that the ciphertext can reach the receiver unchanged. In fact, there might be an attacker who's able to modify the ciphertext as it's being transmitted from the sender to the receiver. And what such an attacker can do is to take the ciphertext transmitted by the sender, modify it to give a different ciphertext C', and forward that modified ciphertext to the receiver. The receiver, of course, has no way of knowing whether what they receive is what was sent by the sender or what was sent by anybody else. And so they're going to take that ciphertext, the modified ciphertext C', and decrypt it. In general, this will give some modified ciphertext, modified plaintext M' that the receiver will then decide what to do with next. What are the concerns in this setting? Well, one concern is that the encryption scheme might be malleable. Okay, this is a technical term that has a formal definition, but that I'm only going to define informally here. An encryption scheme is malleable if, roughly speaking, it's possible for an attacker to modify a ciphertext, like on the previous slide, and importantly, thereby cause a predictable change to the plaintext. Of course, for any encryption scheme, an attacker can always modify a ciphertext that's sent, but in general, that might result in just garbage or some unpredictable effect in the plaintext. But a scheme is malleable if it's possible to modify a ciphertext in a particular way, and thereby cause some predictable modification in the underlying plaintext. We'll show an example in a minute, but first I just want to highlight that malleability can be really dangerous anytime you're concerned about the possibility of an attacker interfering with your communication. So think about the case of encrypted email. If I encrypt an email to somebody else that says, say, I'm willing to pay you $100 for something that you've advertised, well, if an attacker can modify that and change my $100 agreement to buy to something saying that I'm willing to pay $1,000, well, that can have very damaging consequences for me. And similarly, in any kind of setting where you have encrypted transactions, say with your bank, if I want to withdraw or transfer $100 from my account to someone else's account, it would be really bad if an attacker could modify my encrypted transactions with my bank, but thereby cause the bank to receive a message telling it to transfer $1,000 or $10,000 to somebody else's account. So these kind of attacks can be very damaging. If you think about it a little bit, you'll notice that all the schemes, all the private key encryption schemes we've discussed so far, are in fact malleable. For example, the one-time pad is trivially malleable. Here we'll have the picture from the previous slide, but now with the specific case of encryption using the one-time pad. So say we have our sender now taking their key K and encrypting their message, which I've now written as a sequence of bytes, M1 through, bits, M1 through MN. So that means that the sender will take this message M1 through MN and XOR it with their key, which is also going to be n bits long, and obtain some n-bit ciphertext C. C is also represented here in terms of bits, and we can imagine, as before, an attacker who modifies this ciphertext in some way. For example, say the attacker just flips the final bit of the ciphertext to give a modified ciphertext that contains the first n-1 bits of that ciphertext identical to the original one, and the final bit flipped. Well, what effect is this going to have on the message that the receiver obtains when they decrypt? Well, when the receiver decrypts, they're going to take the ciphertext they received, which is going to be the modified ciphertext with the final bit flipped. They're going to XOR that with their key k, and what you'll see is that the first n-1 bits of the message that they recover will be the same as the original message, as those of the original message sent by the sender. But the final bit of the message that they recover is going to be flipped as compared to the bit that the sender intended. So this has the effect of flipping the final bit of the plaintext. So in summary, this means that by flipping the last bit of the ciphertext, an attacker is able to predictably flip the final bit of the plaintext. And this is not limited to the final bit. The attacker can actually flip any bit in the ciphertext, and flipping the ith bit of ciphertext will flip the ith bit of plaintext. And nothing limits the attacker to flipping only a single bit. If the attacker flips any number of bits of the ciphertext, it will have the effect of flipping exactly those bits in the underlying plaintext. This means that the attacker, if he knows anything at all about the original plaintext, can cause very predictable and possibly damaging effects on the recovered plaintext. Now, this is very interesting because it implies that even perfect secrecy, which was the strongest, or which at least was a very strong notion of security that we discussed that does not rely on any computational assumptions, is not sufficient to imply non-malleability. That is, schemes can be perfectly secret, like the one-time pad, but still be very malleable. And the attack that we've demonstrated on the previous slide is not limited only to the one-time pad. In fact, a very similar sort of an attack, and sometimes even other kinds of attacks, are applicable on all of the other encryption schemes we've seen so far. I'll leave that as an exercise for you, but it is indeed the case that every scheme we've seen so far is vulnerable to a similar attack. So coming back to our original discussion, right, we talked about the fact that we might have an active attacker who can inject or modify messages being sent across the communication channel shared by the sender and receiver. Well, let's now consider the second case, that of the attacker who is impersonating the sender and injecting communication on the channel. This is actually, you can view as a special case of the previous attack where the attacker modifies something being sent across the channel. The real difference here is just that this attack can happen without the attacker, without the sender sending anything at all. The attacker can just choose to send messages on its own to the receiver, claiming that they're from the sender. It doesn't have to wait for the sender to do anything. So here the picture might look something like this. Here we have a sender and receiver communicating over a channel, and an attacker eavesdropping and observing some ciphertext that the sender has already transmitted to the receiver. But now, rather than just restricting the attacker to remaining passive, we're going to allow the attacker to additionally inject ciphertext on the communication channel between the sender and receiver. So what the attacker might be able to do, for example, is to send a ciphertext C' to the receiver. And the way it's drawn here, it looks like it's coming from another direction, but this is just the limitation of our picture. And in reality, the receiver has no way of telling whether the ciphertext that it receives is coming from the legitimate sender that it intends to speak with, or from some other party in the network. So anyway, the attacker may be able to send a ciphertext to the receiver, cause the receiver then to decrypt that using the key that they've shared with the sender, with the honest sender, recover some plaintext message M', and then at least in principle, the attacker might be able to learn either M' or some information about M'. This picture should actually remind you of the picture we had in the context of chosen plaintext attacks. So in that setting, we had the attacker, as it were, interacting with the sender, injecting messages or influencing the sender to encrypt certain messages of the attacker's choice. And then the attacker was able to observe the resulting ciphertext. Here, we're just looking at the other side of the diagram and assuming that the attacker might be able to inject ciphertexts to the receiver and thereby cause the receiver to decrypt those ciphertexts and give some information back to the attacker. And this class of attacks, where the attacker sends ciphertexts to the receiver for decryption, are called chosen-ciphertext attacks. And chosen-ciphertext attacks, as I just mentioned, are meant to model settings in which the attacker can potentially influence what gets decrypted by the receiver, and then observe the effects. And just as in the case of chosen plaintext attacks, where it's not clear how to precisely model what an attacker might be able to do in some real-world situation, what we'll do is we'll just give the attacker as much power as we can in our formal definition. So that is, we're going to consider a definition that allows the attacker to submit any ciphertext of its choice, with one restriction, to the receiver, and then learn the entire corresponding plaintext. Now again, this is a very strong definition. This is going to result in a very strong definition that we'll see in a moment. And the point is that this definition is going to capture any kind of more limited chosen ciphertext attack in practice. That is, it'll also capture weaker attacks where the attacker is limited in what ciphertext it can give to the receiver and cause to be decrypted. And it's also going to capture weaker attacks where the attacker doesn't learn the entire decryption of the ciphertext that it gives to the receiver, but only learns some partial information about the decryption of the ciphertext it gives to the receiver. But again, our definition is going to be quite strong and subsume all of those attacks. The other thing I want to mention is that when we talk about chosen ciphertext attacks, we're implicitly continuing to allow the attacker to carry out chosen plaintext attacks. So chosen ciphertext attacks are therefore strictly stronger than chosen plaintext attacks because we give the attacker all the power that it had for a chosen plaintext attack, and in addition give it the ability to carry out chosen ciphertext attacks. The formal definition is as follows. So as usual, we're going to fix some encryption scheme pi and some attacker A, and then we can define, based on those, a randomized experiment that I'm calling here priv CCA. As usual, this experiment is parameterized by our security parameter n. And the experiment goes as follows. First, we run the key generation algorithm to obtain a key k. Then we allow our attacker to interact both with an encryption oracle, as in CPA security, but additionally to also interact with a decryption oracle. And this decryption oracle is keyed with the same key that was generated in the first step and that is being used in the encryption oracle as well. So the attacker can interact arbitrarily and as many times as it likes with both of these oracles. And then at some point, as is usual for these kind of definitions, the attacker outputs two messages M0 and M1 of the same length. A uniform bit B is chosen, and we then encrypt the message MB using our encryption scheme and again the key K generated in the first step. This gives us our challenge ciphertext C. We then allow A to continue to interact with both the encryption oracle and the decryption oracle with one restriction. And that restriction is that we don't allow the attacker to request decryption of the challenge ciphertext C from the decryption oracle. If we had allowed the attacker to do that, then there's no possibility of having any scheme satisfy this notion of security. Now, it may look a little bit weird that we sort of artificially restrict the attacker from doing that, but in fact, this results in a meaningful definition that, as I said earlier, captures any kind of chosen ciphertext attack that an attacker can actually carry out in the real world. So finally, the attacker outputs its guess B prime as to what was encrypted, and will say as usual that A succeeds if its guess is correct, and the experiment will evaluate to 1 in that case. And we'll say that pi, the encryption scheme, is secure against chosen ciphertext attacks, or CCA-secure, if for all probabilistic polynomial time attackers A, there's some negligible function epsilon, such that the probability with which A succeeds in the experiment on the previous slide is at most 1/2 plus epsilon n. This is the exact same format of the definitions we've seen before. The only difference is that we've modified the experiment. We've made the experiment stronger by giving the attacker more power. Now, it turns out that there's a relationship between the definition of CCA security and the notion of malleability. And it's maybe easiest to see by flipping things around a little bit. So I claim that if the scheme is malleable, then it cannot be CCA secure. And this is really just intuition. I haven't formally defined what malleable means, so this is not any kind of a proof. This is just an intuitive sketch as to why this claim is believable. So let's say we have a scheme that's malleable. Well, then that means that we can take a ciphertext and we can modify it, causing a predictable effect on the underlying plaintext. So now I'll show how we can use that to succeed in the CCA experiment. What we'll do is we'll get, as part of the experiment, a challenge ciphertext C. We'll then modify that to get our modified ciphertext C prime. This modified ciphertext C prime is modified in such a way that when it's decrypted, the resulting plaintext has some predictable relationship with the plaintext underlying the original ciphertext C prime. So if we submit this modified ciphertext C prime to our decryption oracle and get back the result, then based on the predictable relationship that it should satisfy, that should tell us information, or that will tell us information about the original message M that was encrypted to give the challenge ciphertext. And so we can then use that to break CCA security of the scheme. The contrapositive of this is that if a scheme is CCA secure, then it must also rule out all such malleability attacks. And so if a scheme is CCA secure, then it also does imply that the scheme is non-malleable. In the next lecture, what we're going to explore is a real-world example of chosen ciphertext attacks called padding oracle attacks. These kind of attacks are actually very clever, and what I want to get through to you by showing them is that chosen ciphertext attacks can come up in the real world, even in apparently very benign situations. And that's going to help motivate why we care about CCA security in the first place.